The title of the webinar today is Optimize the Reinforced, Do Not Waste Steel. This webinar will be recorded from previous webinars. All of the recordings are available on the e-learning webpage. At the end of the webinar today, we'll have 15 minutes for Q&A, and I will conduct it. So we would like to announce we have almost 200 registered attendees for the webinar today. This is fantastic, and we look for your active participation in the webinar. Let me introduce myself. My name is Dolores Pulido, and I have science at the Spanish National Research Council here in Madrid. I'm professor at the School of Civil Engineering in the Technical University of Madrid. And I have the pleasure to act as your moderator for this webinar. So first of all, I would like to present you with some background and context on behalf of IABSE. Next slide, please. Next slide. Yes, thank you. So the IABSE mission is to exchange knowledge and advance the practice of structural engineer worldwide. And this is conducted in relation to all aspects in the structural engineer, all types of structure and structural materials, and all aspects of the construction process. IABSE is a very large organization with over 3,200 members in 100 countries. And you may be aware of your national group, and if not, we'd encourage you to reach it and become involved. The webinar you are going to see today is available by the e-learning platform, as are all the previous conducted webinars. Furthermore, IABSE conduct a number of very high-profile international conferences, such as the upcoming conference in New Delhi in 2023 and the Manchester Symposium in 2024. In addition, next, thank you. IABSE published a number of high-quality publications. You can see our journal, Structural Engineering International, structural engineering documents, case studies, guidelines, conference proceedings. Next, please. IABSE have a large number of national groups and task groups, and we will encourage you to become involved with those. Next, please. If you take a look, we have right now 6 technical commissions and over 40 tax groups. If you're interested in some of them, you can take a look to our webpage. Next, please. If you are a young engineer, there are a variety of resources available to you. You can have free online access to the journal from 1992 to 2023, reduced IABSE conference fees, free books, and reduced price on hard copy. And probably, most importantly, there is a chance to meet international experts and interact. Next, please. IABSE is very active at the national level. As you can see, you can find very different events, technical visit, workshop, conference, seminar, meetings in many different countries. And finally, next, please. I'd like pointing to the e-learning. The IABSE e-learning is the place where you will find e-learning videos, lectures, series, short videos, courses, animation, and animation related to structural engineers. So again, we encourage you to become involved if you are not already involved in IABSE, to capitalize on those resources which are available. So now we are going to take a look to the video of our sponsor, Enrique, if you don't mind.
There's always a new day, a new beginning, and a new challenge in IABSE Group. We are specialized in detailed engineering, supply, transformation, prefabrication, and installation of passive reinforcement in concrete structures worldwide. IABSE Group has worked on the most outstanding projects in the world: tunnels, bridges, airports, highways, hydraulic projects, maritime projects, railway projects, wind farms, hospitals, buildings. At IABSE Group, we can shape your structures and make them a reality. We have created a model that adds value to each project through engineering, an industrial model, and our own building system, which allows us to offer custom solutions and prefabricated elements that reduce execution time and auxiliary means on site, as well as minimize costs. All of this while maintaining the highest quality standards and guaranteeing the safety of our workers. We have our own machinery, highly qualified personnel. We always bet on innovation, and we are committed to permanent improvement. We maintain strategic alliances with global and local steel providers, supplying special products according to each design's needs. Our planning process allows us to have live tracing of each order's progress and to guarantee the precise delivery of the final product. We are a multinational company with a vocation for local development. Our objective is to create change and progress in the places we operate in. We accompany our clients in achieving their goals, providing the best time and resource optimizing solutions as we fulfill our commitments. IABSE Group. Creating structures, bringing people and places together.
Very interesting video. So I would like to introduce you the speaker of today, el profesor Enrique Hernández Montes. He's professor of structural engineering at the School of Civil Engineers of the University of Granada. Enrique is going to invite us to step out of our comfort zone, convincing us to use asymmetric solution in our daily reinforcement solution. Is that right, Enrique?
That's right, Lolo, that's right.
So Enrique, the floor screen is yours.
Okay, thank you. Yeah. Okay, yes, I'm trying to convince you to optimize the reinforcement in your daily designs and do not waste steel. So reduce your CO2 emissions. Let's go. I'm going to share a presentation. So can you see that, Ronnie?
Perfectly.
Okay, so the title of today's presentation is, as said, optimize the reinforcement, do not waste steel. And I'm going to try to convince you in 3 jumps, like an acrobat. No? So modifications that are always necessary in construction, a product that IABSE is installing the name is non-symmetrical piles. And then the 3rd jump is, in general, the use of non-symmetrical solution. Let's go to the first easy jump, modifications, that, as said, are always necessary during construction. So when we use construction drawings in our design, likely, in particular, in what is related to the reinforcing strategy or the reinforcing cases, the shop drawings used to be very different, because the shop drawing, they accumulate all the knowledge, because they, when you construct, you have to take care of the manufacturing procedure. If you use templates, what is the tie and the welding strategy? You need to think in the transportation, in handling, of course, lifting a cage is something very important that you do it properly, or otherwise you can damage the cage. So the materials availability, this is also, otherwise it can be, the reinforcing can be a bottleneck, in the work. So you need to know if you are using coils or bars, or the amount, the speed of them. So likely sometimes you require even new design. Let's see with an example. So this is one of the factories of ERSI, and this is one original design. So it's a pile with 2 layers. As you can see, 2 layers of reinforcement. This is the original design. The pile is 2.5 meters. As you can imagine, this is hard to construct because the size is very large, and the machines like these, they used to fabricate just 1 layer at once. So at the end, what ERSI in this case proposed is to build 2 layers and then introduce one into the other. No? And then once you have introduced the smaller one into the big one, you have to move so they are concentric, no? And then fix them together, as you can see in this picture at the right side, which is already lifted and just ready to be loaded on the truck. No? So let's show a small video where you can see how one of the cages is introduced into the other. No? So. So in this case, it's doable. So you can introduce one into the other. But in order to do the design, for example, of this proposal, the most demanding parameter of the key parameter was the size of the roller. So the roller is such that when the roller is introduced into the large case, into the large cage, and then when both cages are fixed, you have to be able to extract, to take out by hand each one of the rollers. So that was really the most important parameter to fix the design. So this is, for example, the proposal by ERSI, so 2 layers, and this is the original proposal. And at the end, you have to justify them numerically, in this case with PM interaction diagrams, like the one you can see here. So yeah, this one is the nominal values, and this one is with the phi factors, because this is done with the American code. So you can see here the tension control zone, this is the compression control zone, and this is the intermediate zone. So at the end, for example, that was justified just only by capacity. So the proposal has to include inside the original design. So that was done with an additional bar, of course. But also not only that, so not only the roller, you have to know which is the template that you are going to use. For example, in this case, this is one of the templates of ERSI. You can see that the coordinates of the bars are fixed, different from this one that I took from the web. That it's more flexible, but at the same time, you can see that the one on the left is really more robust. So you can easily imagine that this template has done thousands of piles. No? So that is one of many more examples. No? So mainly these examples are done to save steel and to make the manufacturing process easier. So that was the first jump, modification. So it's like introducing you to the fact that the engineering design is not finished when the project or the design project is finished. It's a continuous progress during the construction. So the next step is a product that is called non-symmetrical piles. It is used for earth retaining systems. So imagine that you have this wall of piles here, and it has been constructed in this way. So it's just like, the same bar, equally spaced around the perimeter, so that we call symmetrical reinforcement. But as you can see, or you can guess here, the bending diagram will not change the sign. So it is like, that is, in some section, that will be the most optimal layout, and in other section, that will be the more optimal layout. So, for example, that is the underground metro in Riyadh. This is line 6. So the original project considered this wall of piles with 2 props here. You can see, and then the train goes here inside this concrete box. So, and this is the final work. So the final work, all was done with non-symmetrical piling, only with one line of props. Yeah. So in different with the original. So that was a change, but also was changed the reinforcing. So there was original project with symmetrical pile, and all their thousands of piles were done non-symmetrically.
Enrique, just a curiosity, who proposed the change from 2 levels of frost to 1 level?
No. In this case, the props or the change of prop was proposed by the geotechnical department of the construction firm, and we only propose. You know, ERSI is focused on reinforcement. No, so we propose the change to non-symmetrical pipe. So, for example, this is the non-symmetrical pipe. No, you can see here in the desert of, well, not in Rihan. So you can see that there is a base of bars symmetrically spaced, and that is with a smaller bar diameter. And the capacity without the reinforcement, you can see here. So these green lines are the bending moment envelope, or the envelope of bending moments. So the capacity of the base, so only with the small rebars, is this that you can see here. Is the shadow area that you can, so the shadow zone, and this dark shade. This is the capacity. So now, because of all this zone here and all this zone here, they need more reinforcement. So you add the additional reinforcement. In that case, for example, that's a different strategy from the previous that we have seen. So in this case, the additional reinforcement was introduced, you know, once the base was done, no? By hand or by some kind of easy crane.
So another question, Enrique, I imagine that the bending moment diagram is given by the designer. Is that the case?
Yeah, of course. I mean, for example, in the previous example, we can do the adjustment only based on capacity. So when we propose, for example, this in 2 layers, you can do that. We can do that based just with the original design with no analysis of calculation, or not. So that's something. But in this case, of course, we need the bending moment envelope from the designer. So that is, I mean, we when I say we, I'm saying ERSI. I feel part of them. Yeah, we need the calculation in order to propose a change like this. Yeah, definitely. So yeah, this is the pile, and these red lines here. One is for the shift rule, of course, and then the other. So this segment is. This segment is for the shift rule. This segment is for the anchorage, and this small segment here is safety length. So there is a safety coefficient because of the position in length of the pipe. Also, there is an additional error that we can do. So we can have an error, an angle, an error during the placement. So we can rotate somehow a little bit the pipe. So we have to consider that and to fix what is the margin that we have. So, for example, in this case, as you can see, these big bars here, if I have a small rotation, some of the bars gain lever arm, while other bars just lose lever arm. So at the end, the capacity of the bending moment is reduced when you have this rotation, no? But it's very smooth at the beginning due to this effect. So because this gain lever arm and the other lose, so the loss of bending moment capacity is very small. So definitely, for example, in this practical case, we had an available or error of 20 degrees. So of course, once you install them, you can see that you never will reach that. But nevertheless, in the proposal, in the calculation that we have to justify, we have to add what is the margin of error of each one of the piles. Okay, next is a paper we published just a few months ago in the ACI Structural Journal. So if you want, look, Loli, this is your lab. So we did experiments in your lab, Loli. We did there like 10 piles, short-term loading, and the long-term loading, we did that in our lab here in Granada. So what we did here with these tests is to have an expression of the effective moment of inertia, so you can calculate the deformation of this kind of piles. And we use that based on the American formulation of the ACI, well, the old one, the Branson one, which is, I think that since 2019 they changed for this new one, but we are very romantic, we like the Branson formula. Even it's not from Branson. It has been used from the 20s, so it's almost a century old. So the point is just, an interpolation between the crack section and the gross section. And this interpolation, there is two coefficients here, depending on the, well, whatever. I am not going to explain here to use. It's just basic concrete structure course. But the idea is that we experimental fix this M value and this beta value. The beta is a coefficient that takes account the amount or relative amount of non-symmetrical steel that we use. And this is, we did, the black points are tests, and the white points are finite element models, very detailed. So you have here from a few months ago for the public, a way to calculate deformation of this non-symmetrical pipe, which is very important, of course. And then numbers. So this from the earth engineering department, just to see really an example in numbers. So pile 5A, one of the piles in the underground line 6 in Riyadh Metro. One of the piles, the 5A, were more than 1,000 of these piles. And the longitudinal reinforcement was 17 bars of 32 millimeters. And the transversal reinforcement was 12 millimeter diameter, spaced 20 centimeters with a length of 25 meters. The original drawing that never was constructed was more than 3,000 tons per, more than 3,000 tons total, but 3 tons per pile. The number of couplers, mechanical couplers for each pile was 34, and the total of couplers in the original design was 35,000 couplers. What we installed there, what IABSE put there, is the non-symmetrical solution. The weight per pile has been reduced from 3.3 tons to 1.9 tons. The total is 2,000 tons versus 3,500, no? And the connectors that we used was none of them. So we reduced all the connectors. So at the end, the steel reduction was 1 ton per pile and a total of reduction of around 1,500 tons. So it's a 41% of the total reinforcement of each pile. For each pile I am referring to 5A. And the number of connectors, all of them. So the 30, we saved 35,000 of connectors. And more of everything is that we avoided the emission of 3 tons into the 3 tons of CO2 emission into the atmosphere that we didn't do. So the idea is, actually, let me tell you an anecdote. When I was presenting this to FCC, the construction firm, one of the old structural engineers, he's already retired, told to his partner, remember this, because in the future we will say, remember when we did symmetrical piles for earth retaining systems? So I invite you, Loli, and the audience to feel guilty if from now on, in the future, they construct walls, piles symmetrically. So do not sleep at night. Your conscience will tell you that you are a sinner, you know, or sorry. Yeah, so yeah. I hope if you do it, you don't sleep during night. Right, Loli? Is that enough? Feel guilty. Anyway, so that is this is a really nice product, and I think we are obliged. We have to use it. Okay, the third jump, I hope I am convincing you. So the third jump is going to unsymmetrical. So we are just going to fly, unsymmetrical. And to do that, I'm going to introduce you what is the reinforcement sizing diagrams, or RSD. It's a tool that we use in ERSI. For example, when you have, precast tunnels like this, precast buried structures, like this one, many times, for example, in this side wall, people use, or we have used, symmetrical solution for the reinforcement. So at this point, let me take to class. So I recorded a class. I'm going to show you. It's like 15 minutes class. I know, Loli, that you don't like empty classes. It's empty, but you are now the public. So let me just stop sharing this. I'm going to share the class with all of you. How is this going, Loli? I'm convincing you?
Sure.
Okay.
No problem.
Or you are easy to convince?
I am easy to convince.
Okay. Okay. Can you see this?
Okay, so we are going now to introduce something very simple, which is the reinforcing sizing diagrams. We also name that like RSD. And it has to do with the ultimate limit state of bending. So something very common in reinforcing, in reinforced concrete. So let's start analyzing a cross section. Let's be original, a rectangular one. So the height is h, the thickness or the breadth is b. Everything is, so very standard, no? So the top reinforcement is SI and AS prime. The bottom reinforcement is AS. The mechanical cover of the top reinforcement is D prime, and the distance from the top fiber to the bottom reinforcement is D. So this is all very international nomenclature. So now we are in ultimate limit state of bending. So the strain distribution, and I'm going to use the American just for simplicity. The European is a little bit more complicated. Nothing very difficult, but let's do the American. So the ultimate strain, because this is positive bending, so the ultimate strain in the top fiber is going to be 0.003. And then let's do a general strain distribution. So general strain distribution, this is X. This is X. The depth of the neutral fiber. So any of these planes are capacity planes, so they are, all of them are the ultimate limit state of bending. But let's do, we are going to work with a generic one. So this one, the depth is X. So for this, because we are in capacity design, and we know that the top deformation, the top strain is this, 0.003, we only need one variable to fix the strain distribution. This one variable is going to be X. So if I know X, and I know that I am in the ultimate limit state of bending, then the strain distribution is fully defined. So this is, let's do another color, for example. So this is the strain of the top reinforcement, and this is the strain of the bottom reinforcement. So this is epsilon S prime, and this is epsilon S. Okay, perfect. Once I know this, and this is going to be the strain. Sorry if this is very simple. This is basic course of mechanics, but okay, let's continue. So if I know the strain distribution, it's simple to get the stress distribution. Because we are going to be in the ultimate limit state of bending, I can use the rectangular distribution of stresses in concrete. So that means that I am going to consider that is under compression only lambda x, and the value of the stress is FCD. So this is the contribution of concrete in capacity. Then here we are going to have sigma s, and here we are going to have sigma s prime. Let's put that in compression. So this is going to be sigma s prime, and this is going to be sigma s. It is very easy once you know epsilon s to know sigma s, because this is just only, for example, the bilinear diagram. So the bilinear diagram from Eurocode, so that epsilon s, sigma s. So once I know epsilon s, maybe here, I know sigma s. But because everything is defined by x, epsilon x is a function of x, epsilon s prime, and epsilon s is also a function of x, and sigma s prime is a function of x, and this is a function of x. Because once I know x, I know the strain distribution, I know epsilon s and s prime, I know sigma s and sigma s prime. Perfect. This stress distribution has to be in equilibrium. Let's do that. This is the center of gravity of the cross section. So it has to be in equilibrium with, and well, we are in capacity. So let's do here NRD and here MRD, the resistance design, so capacity. Let's write the equation. Let's write the equation of equilibrium, the equation of equilibrium. They are going to be very simple, and we all know that by heart. So NRD, the actual force, what is going to be? Is going to be FCD times what? Times lambda x times b. Okay. And then plus sigma s prime is a function of x. We all know that. Times AS prime, the value of the steel in compression, minus sigma s, function of x, and then AS. Okay, something happened here. And if we have the actual force, or the bending moment, sorry, MRD, so it's the same, but with the corresponding lever arm. So it's going to be FCD times lambda x times v, and now the lever arm is going to be h over 2 minus lambda x over 2. Yeah, so perfect. Then this is going to be sigma x, the contribution of the top reinforcement is sigma s prime function of x, as prime, and then the lever arm is going to be h over 2 minus d prime. And then the contribution of the bottom reinforcement is also positive. So this is going to be plus sigma s of x, as, and then the lever arm is going to be d, no, d, right, d minus h over 2. Perfect, perfect. So one thing that we all know is the PM interaction diagram or NM interaction diagram. So the NM interaction diagram is something very simple. We all know, because all engineers, what we really know or we have in our soul is the NM interaction diagram. It's just the representation of the capacity for a cross section. So let's say AS, so we have a cross section, AS and AS prime are known, the concrete is known, the geometry is known, so everything is, so in here the only unknown is X at the right side of the equality. So here at the right side of the equality the only unknown is X because everything is defined. So what we do is a representation of M and N that should be like something like this, for example, and something like this. Yeah? It's non-symmetrical, so if it should be like this maybe. Okay, more or less. So just giving values to X, and in this is from X to 0 to X to infinity, or very large. And then we obtain for each value of X pairs nm. So for each value of X, we obtain the whole diagram. This part is for positive bending, and the one we have considered here is positive bending, but if we consider negative bending, we obtain the other part. This is very interesting because if we have a bunch of combination of pairs nm, we know that the section will resist or not all this. If we have one of these out of this, it will break the section, and the section will not resist this pair. So we all know that. But let's go in now at this point introduce what is the RSD. Imagine that we don't know AS, and we don't know AS prime and AS. We don't know them. And imagine that N and R are given. So in these two equations, now we have three unknowns, which are X, AS prime, and AS. So we can solve for AS and AS prime. So we can solve for AS and AS prime. And we discovered that once we solve for them, what we obtain are function of X. So we can say that AS and AS prime are function of X. So yeah, if N and M are given, I can solve these two equations for AS and for AS prime, and what I obtain is function of X. I can write here solving for that. I don't know if it is worth to do it or not. It's published already, so just find in publications. We have published the solution, so don't worry. Or you can just spend time and solve for that. There's not much interest. So the idea is that you can plot here X, and here you can plot the area of steel. So, and we are going to have three plots. One, for example, is AS prime, can be like this. AS prime. We can have also, I'm just, for example, this. That can be, for example, AS. And then the summatory of the two of them can be like this. So this is going to be AS plus AS prime. What we obtain is that a solution can be for AS prime equal to 0 and AS equal to the total area, so we only have AS. Or we can, for example, opt for the symmetrical solution, but the symmetrical solution is way more expensive in money and in CO2 emissions than the minimum one, that in this case AS. So we can look to all the possible solutions because we don't gain anything. So we gain nothing if we design for the symmetrical, because the ultimate bending moment and the capacity is going to be the same. So let's do an example, because this is very useful in some type of structures. So imagine that we are doing a precast tunnel. So we have here, piece of land. We do a trench here. We do a trench here, and then we design here a precast tunnel, something like this. Then the symmetrical here, okay, that's symmetrical. And here, for example, the roof. And here is just symmetrical. And then we feel that. So in a cross section like this, I'm going to have a huge moment, a huge bending moment, and a huge axial force. And many of our colleagues will say, okay, big axial force, symmetrical reinforcement. And you know, I deal with this topic very often. So please, you know, just use this. You know, don't, you know, I know that we all love PM interaction diagram, but for cases like this, where the worst case scenario is very clear and is just likely 1 or 2 or 3 pairs NM, do an RSD, and you can see, you know, where the minimum is. And we can save tons of steel. Actually, you know, for example, if we do, so this is the thickness or the breadth of here, no? So that's the breadth. And we opt for the symmetrical solution. What we obtain is this depth of the neutral axis, for example. So this. So if I just don't use AS prime, the only thing is that X is going to be a little bit greater. That is the only thing. So the only consequence is that X is going to be a little bit deeper. But I don't need that. Maybe because of construction, I'm going to put here some minimum amount. Okay, perfect. If I put here some minimum amount, I can go for this, for example, in AS. Okay, that's the only thing I wanted to tell to you. Thank you.
So, okay, Loli, I hope you got not very bored.
Yes,
class.
just a curiosity before.
Okay.
Can you do the same with the PM interaction diagram?
I don't know. Yes, you can do with PM interaction diagram, but the point is that mathematically it's a not well-conditioned problem. So you can try and never reach the minimum. So the nice of RSD is just you have all the possible solution in just one graph, and that's, you know, I would love to see memories of, you know, the justification, the analysis justification in project with this new graph. Or, well, it's not that new. We created this years ago, but okay. Let's continue with the presentation.
Yes.
It's almost finished, so don't worry. I'm not going to be paying. So I hope you already know the size reinforcement RSD, reinforcement sizing diagram. Actually, this is a real case, the one that we saw now in the blackboard. And this is the case. So this is the summatory of the two of them, the total area. The green is AS prime, AS, and this is the same case. So you can see that this is in the horizontal axis is the depth of the neutral axis. So the only thing when you opt for symmetrical solution is that you reduce, you have a smaller depth of the neutral axis, just with a bit more, you know, with a bit more of concrete working in compression. You don't need the AS prime. Actually, I remember in Newmark, one of his book, Newmark is Newmark, you know, the top guy in the father of earthquake engineering, you know. So talking in one book that when you add compression reinforcement, you increase ductility. Well, yes and no. So I mean, the point is, if you put just freely steel in compression, what is the purpose for that? So the idea is that, okay, the idea is, I think that Newman didn't get the comparison. So the real comparison should be, what is the capacity? Because if I add compression steel just for free, of course, I am increasing the capacity, but that's not the idea. Well, anyway, RSD are not only this shape, they can be this shape. You can find all this that I said in the Blackboard, and they developed in this paper that we published years ago in ACI Structure Journal, design of concrete members subjected to uniaxial bending and compression using reinforcement sizing diagram. I published it with Professor Jill Martin and Mark Ashane. And you can see here, for example, this is another case. You can see here see the minimum, and this is the symmetrical. So there is a huge difference sometimes, a huge difference that you should take advantage. You cannot just use symmetrical for free. Okay, this is ACI code. So all this in Eurocode should be softer, but in ACI is with the phi factor. So this is already affected by the phi factor. Okay, this is another version that we have been working on that, but as far as I know, never used so far in practical, is that also we did something we call biaxial RSD. So when you have a column like this with bars in the perimeter, you can opt for different separation in different sides, well, in parallel sides, and you can get some kind of RSD like this one with a minimum. So for example, this is total reinforcement versus top and bottom reinforcement. So this is another way. Let me now, sorry, to make publicity of myself. So all this way of little more mathematical reinforced concrete, little than so far. So we are going to publish a book. It will be in the bookstores, I guess, in a month or two. It's published in the CRC Press of Francis and Taylor. The name of the book is Concrete Structure, Design and Residual Capacity Assessment. And I'm going to publish that with Professor Jill Martin. It's the second book we have in this collection. So previously, 4 years ago, we published another one, and the title was Design of Reinforced Concrete Buildings for Seismic Performance, Practical, Deterministic, and Probability Approaches. I wrote that with Mark Ashane, and I present this book here because today is 4 years ago, Mark Ashane passed away. So I lost really, I think, my greatest friend. He was an outstanding guy in earthquake engineering, definitely. I published that also with Dimitrios Pasikos from the Technical University of Athens. Dimitrios is a PhD from Stanford. He did his PhD with Cornell. And I think that in probabilistic analysis of seismic performance, I think is really top one. Mark actually was a PhD from Berkeley. He started his teaching career, his academic career in teaching in University of Illinois. And when he passed away, he was professor at Santa Clara in California. So somehow the speak of today is in honor to him. Thank you very much for inviting me, Loli, and all the IABSE organization. Do not hesitate, email me if any question, please. I will love to see, structure community is very small. So at the end, we all are almost friends. And also you can write to RC Group for any of his or their products and whatever curiosity. And thank you, Loli. I hope that was the stage now is yours, not mine anymore.
Thanks to you, Enrique, for sharing with us your knowledge. Before checking for questions, we have many questions. Let me see if I've understood. So RC sells steel, manufactured steel, and you are proposing buying less steel, right? So is there any trick to it?
You think they are going to kill me?
No.
Sorry, that's a joke. No, RC really what they sell is solutions. So RC, as you know, I have been joined to them. Let's say we sell solutions. We are partners in the construction. So that is the reality. So if the client is happy, you know, and the work was well, and we even do not cooperate in the greenhouse effect, that is the point. No? Let's be good guys and good engineers. No.
Okay, so we will start with the questions in the question and answer box you can find at the bottom of your screen. Sebastián Artes Payán asks many questions.
Wow.
I read it together. Very interesting. Thank you, Enrique. Very interesting. Don't you think that it will require additional supervision? There is a reinforcement, putting reinforcement in the pile in the wrong direction. This method is applicable for underground structure mailing, isn't it? So
okay, Sebastian, thank you very much for your interest and your very, very interesting questions.
Yeah.
Definitely, you are right. So it will require additional supervision. Let me tell you one anecdote, because that explains a lot. The first time we did this, we did an experimental segment in the high-speed railway in Barcelona. You know, Sants, Barcelona, near Sants station. So we took there 10 piles, 10 non-symmetrical piles to see the deformation compared with the symmetrical. The project manager told us, can we do everything like this? Because it was easier to construct. It was really cheaper, and it was really easy to supervise. Actually, also a professor from Madrid came to me to see this rotation, came with us when we were constructing these piles. And, you know, with a little bit of care, of course, it's a protocol. You have to follow another protocol. But what we gain in terms of reducing CO2 emissions, money, is a lot. Each pile, Sebastian, in the pile that we tested in Barcelona, was 10,000 kilos per pile, the difference. So I think that you can supervise with this. And that is your fair question. Of course, there is a risk if you do it in the wrong direction, but it's just a way to supervise. You know, that is. It's applicable for underground structure. Yes, but you can be surprised. Earth retaining or even water retaining. So, for example, hovers is a huge application that we are studying now, and we are proposing. I hope. That is okay. I don't know. Any more question?
More question? Yes, sure. From Stefano Micoli. Sorry about pronunciation. Thank you for the very interesting speech. The reinforcement reduction in the Riyadh metro is impressive. Is the non-symmetrical piles method under any patent, or is free to use?
Okay, Stefano, thank you very much. Very interesting question. Let me tell you. So we patented that, or we were granted the patent many years ago. I think in 2003 or 4, I don't remember, by University of Granada. So when ERSI came to us, to the university, he said, well, I'm interested in this product. This will be really good for us. And we studied, and the patent was over. So let's say that the patent as design is over. You can freely use that outside of Spain. So things that happen with patents, no? But that also additionally, we help ERSI to do two new patents in terms of construction procedure. And I answered this also to Sebastian. There are patented construction procedures for that ERSI has. That is the question. And I mean, that is the answer. Sorry.
Okay, thank you. More questions from Anastasia Moskaleva. I'm not sure if I pronounced right. Can we include non-symmetrical piles in our designs?
Anastasia, yes, I think yes. You can introduce non-symmetrical pile no problem. Just one thing to warn you. Now, UGR, University of Granada, with ERSI, we are working now in doing a software. So by the end of the year, I guess, more or less, so give me some extra months, but by the end of the year, we will have an available software that will give you the calculations and also the drawings. That is the idea. So by the end of the year, things will be even easier. So you can just click and obtain your non-symmetrical solution.
Okay, so Anastasia asks again the same question, if there is any pattern, so we don't have to. Another one from Lucia Matei. Thank you for the great presentation. Have you used the solution for bridge abutments also, non-seismic regions?
Bridge abutment, not so far, Lucian, not so far. We have used, as I think Sebastian said, more is earth retaining, and also large number of piles. This is really very attractive when you have thousands of piles. So cut and cover, earth retaining, harbors. This is not only earth retaining, but also water harbors. So thank you.
Okay, from an anonymous attendee, where can we access or buy the books you have presented?
Oh, yeah, I mean, earthquake engineering, the earthquake engineering book from Mark Action and I, you can buy Taylor and Francis, you can enter there at any bookstore. It's a more or less well spread book. Actually, I think it's a very good book. Both are very personal in the sense that, for example, our concrete book that will be available in a few months is a very personal. It's a little bit more mathematical than but it's worth to use it because it's yeah, as I said, very personal. It's based in Eurocode 2, but also treat other codes. For example, the formation, it has to. We use a lot. We use a lot American code, but also we use fiber elements. Many of the problems are solved with OpenSys. I think it's a really well. I'm sorry. I tried my best. So if you don't like, email me and say, Enrique, fail, a disaster. And yeah, so Taylor and Francis. Thank you for question.
Okay, and now it's not question, it's just a sentence from Fran Torres. Hello, Enrique. Probably you will not remember, but how to forget you. You were my teacher in the Granada University in 2013 or so. You are a legend. Great presentation. So you have
Fran,
many fans.
Thank you, Fran. You flatter me, and not that much. I try to do. So thank
another,
you.
Sorry, another from Fauchel RB chat. Thank you, Enrique, for this great presentation. The solution was very clear. Many thanks. It's just a sentence.
Okay, thank you.
From John Alexander Velasquez Arias. Thank you for the presentation. How can apply the artificial intelligence to optimize the reinforcement and do no waste still?
Wow, Alexander. I mean,
Yes.
sorry. I have been so disappointed recently with ChatGPT that I don't know if to trust these things anymore. I think it's, I don't want to recommend my book. I mean, okay, it's a good book, but try to go this way. It's a little bit more mathematical. I mean, you don't need, well, I guess you don't need, at this stage, the only you need is to have clear the mechanical problem that you have behind. I encourage you to change all the parameters to be unknown and explore that mathematically. I mean, more than artificial intelligence. Let me recommend you a software, Mathematica. Mathematica is a software that really, I love it. Most of this has been developed in Mathematica already, also translated to other software, but Thank you a lot.
Okay, so no more questions. Thanks again, Enrique, for your interesting presentation and for sharing your knowledge with us. Thank you, everyone, for attending and joining online. And have a nice weekend.
Okay, thank you, Loli. You too.
Okay.
Thank you. Thank you. That's all. Thank you all.
Okay. Thank
Bye.
you. Bye.
Bye.